Hello, everyone. Come on in. Hello, everybody. Come on in. Sorry I wasn't here early this time. I was doing some last minute stuff to make sure we're all up to speed. Anybody have any questions before we get started? It's a good time to
I
ask.
have I have one.
Yes, go for it.
This is chapter. We're going over chapter 3 in this one, right?
Yes. Yes, we finished chapter two last time, but
Okay, because
you're
I thought
open to ask
we
questions.
talked about kinematics last time, which that was chapter 3. Kinematics is chapter 3.
Kinematics chapter two. Chapter three is vectors and projectile motion.
Oh, so wait, so the textbook is off.
Not that I
Oh
know.
no, kinematics in two or three dimensions, vectors. Never mind.
Oh yeah, gotcha. It did say kinematics. I completely forgot about that.
God dang.
Gotcha. We're
Sorry.
mostly focusing on the vector part today, but we might be able to get some projectile stuff done. Anybody have any questions on anything else, including, like I said, this is a time where you get to ask questions about chapter one or chapter two homeworks that you've had that stumped you or whatever. Or of course, you can always take a screenshot, and I highly recommend this. Take a screenshot of either your mastering homework or of your practice test problems. Any problem you run into that you're not really sure of, or don't know how to get started, or got started but didn't get the right answer or whatever. Take a screenshot of it so I can see not only the question, but if it's multiple choice, I want to see the answer choices as well. And feel free to text that to me, and I'll answer it as quickly as I can. But like I said, you can also do it during this class time. So, anybody have any questions? Oh, I just did my commercial for Burger King. Woo! I'm going to be rich. All right. Well, it looks like no one has any questions. I will probably ask you a little later to chat me your first and last name, so you need not do it yet. You're welcome to, but I might ask you to do it again later. It really doesn't matter too terribly much. Like the main reason I usually wait is to see, if students are actually staying. But to be honest with you, I never take points off for attendance or anything like that. And I also don't make a point to, grade people or, give them the benefit of the doubt if they're, point one short point of a A. I don't say, oh, well, I saw that student leave a lot or something like that. I don't keep track of such things in my environment, in my world, when I'm teaching a college level physics course, I sort of allow you all the freedom you want. You could literally, if you kept me in the loop, you could literally never attend any of my classes and just show up for the actual test days or whatever. And if you did all the tests and got all the homework done and all the grades done and made an A, I'd be completely happy with you having an A. Even not attending. So I just want you to remember that these classes are for you, but if you're brilliant enough to do it without seeing the classes, then go for it. It's okay. Uh, I will applaud you. Okay. I will tell you that 241 is a lot easier to do that with than 242, but it's still not easy. We're going to be doing a lot of integration, a lot of integral calculus, a lot of differential calculus, stuff of that sort, related rates, chain rule, all that good stuff. So you might need my help. Okay. So again, it seems no one has any questions, so we'll get started. Uh, what actually, let me go ahead. I'm going to open up my particular page for your class. Specifically, I'm going to open it up so I can see the textbook for anything I might need. But the main thing I want to be able to do is I want to remind you how the chapter starts, that sort of thing. They always start with a chapter opening question that I highly, highly, highly recommend you actually take the time to answer that question. I don't want my students being afraid of getting a wrong answer. I don't want my students to be afraid of answering incorrectly, especially in a face-to-face situation. So, sorry, I'm doing 15 things at once. Probably should be doing one. But either way, what I'm trying to teach you guys is to make a hypothesis. Ideally, I'd want you to think about it reasonably about what you think the answer would be to the chapter opening question. And I want you to apply as much physics as you know at that time to try to guess it. But if you don't even have a clue what physics is related, just take a poke, just take a guess and throw that out there. And then later on, when you get into the section in the chapter where they cover it, correct your work because it really is valuable to make a prediction, see whether or not your prediction is correct, and then adjust your logic therein. So definitely continue doing that. That's the same thing when you're doing labs and stuff like that. I definitely want you to take chances, and I don't want you ever to think that a failed or incorrect hypothesis is in any way bad. An incorrect hypothesis teaches us way more, at least historically, than a correct hypothesis. So just keep that in mind as you progress forward in your science career. So, as one of your classmates said, chapter 3 is called Kinematics in 2 or 3 dimensions and Vectors. And what we're doing with this is the sections are called Vectors and Scalars. And section 3.2 is addition of vectors, graphical methods. 3.3 is subtraction of vectors and multiplication of vector by a scalar. Section 3.4 is adding vectors by components. Chapter or section 3.5 is unit vectors. 3.6 is vector kinematics. 3.7 is projectile motion. 3.8 is solving problems involving projectile motion. And 3.9 is relative velocity, which we sort of already discussed in chapter 2. And like I said, the chapter opening question is another good one that you should answer. So I highly recommend you do that. And let's get moving on. So what I want you to understand with regards to vectors is vectors, like we said in Despicable Me, do have a magnitude and direction. So the writers were correct on that. That is a sort of definition of a vector, but it's a little bigger than that. In fact, what you'll learn as you get further along in classes, maybe taking linear algebra, especially a really, a good level, third year level linear algebra course that's calculus based, something like that, what you'll see is that all those rules that you learned in algebra, that in some cases your teacher taught them to you and then you use them to solve equations. Like, what is one of them was any equation for a equals a, you can multiply both sides by a constant and it won't be affected. Or for every number x, there exists an additive inverse negative x such that x plus negative x is equal to 0. And the distributive property and the commutative property and all those different things that you took as properties before, what you're going to find out is that they are in fact the properties that define what we call a vector space. And when you adopt those rules for anything that you have, not just numbers, but for vectors or arrows or stuff like that, then what you've created is a vector space. And you can prove that it's a vector space. And then once it's a vector space, there's a lot of other things you can learn from it. So that's the big picture of why you had those weird little properties in algebra. And what I need you to understand is that, yes, the definition of a vector being quantity that has magnitude and direction is consistent, but it's not quite complete. It's got to have a lot of other things. So, for instance, it has to be an element of a vector space, which you'll learn later in linear algebra. Again, if you take the calculus based linear algebra, sometimes the linear algebra class is more, linear algebra class, excuse me, is more computational, where you're just doing a lot of matrix calculations and stuff like that. That's not necessarily, I mean, it's extremely helpful for people that have to do a lot of work with the matrices and need to learn matrices and stuff like that, but it's not the theoretical opening of your brain to higher ideas and math like the calculus-based one is. So highly recommend taking that as well. Uh, but when we go from the idea that a vector is a quantity that has a magnitude and direction, it also has very specific transformation properties. So if you go from one coordinate system to another, there's a very specific way that that's supposed to transform. If it doesn't do that, then it's not a vector. It might be a pseudo vector, it might be nothing. But the main thing is it has other things other than just magnitude and direction. The good news is, far as the class goes right now at the 241, 242 level, you don't really need to know all that stuff. Okay, it's going to come and it's important, but it's not all that important right now. So right now we can sort of pretend like it's okay to just say something that has magnitude and direction has to be a vector quantity, and then we can talk about how we add them and subtract them and do other operations with them. So first off, I want to explain to you a metaphor for vectors. So if you imagine each little jaunt of a trip that you take, let's imagine you're walking out your front door and you're going to go for a walk. Okay. Each little, or one way of thinking of it, anyways, is each little straight line path that you walk along creates a vector. And that vector would point from where you were initially until where you came to a stop or where you stopped going in a straight direction. So you can imagine walking from here to here, and then the vector which goes from here to here would be a vector that represents your displacement, how much you moved. Okay. If you do that for each little straight segment of walking you do, then it turns out at the end of all that, a vector pointing from where you started to where you ended up is in fact what we call the resultant or the sum of the vectors. So let me draw a picture so you'll better understand that. So I'm going to share my screen with you guys. Okay, so let's imagine for a second that this is your house, this is your porch, this is your sidewalk, this is the road that your house is on. Let's say maybe this over here is another road or a driveway or something like that. I'll erase this just to make it a little more clear. Uh, and let's say X is where we start watching you. In other words, you're at the position X and we're going to watch you. Okay. So if your first inkling or your first decision you make is to walk from X straight down the sidewalk to the, excuse me, straight down your walkway to the edge of the road, then you will have a displacement vector right there that I'll call D1. Now we normally indicate vectors with a letter, a capital letter, and we normally put a little arrow over them. And as one of your students asked the other day, the direction that you draw the arrow doesn't matter. I've seen vectors written like this, like this, like this, uh, all sorts of stuff. So all of those are completely acceptable. I've even seen them written like this, but that means something very specific. That one specifically, when it's got that little hat on it, is understood to be a unit vector. So its magnitude is one, not 1 Newton, not 1 inch, not 1 meter, but the unit one is its dimension, is its length. Okay, so those are the various ways you can write vectors. And what I just did was I showed you a displacement vector where you walk from X to, let's say, this point right here, which is X2. In this figure, D1 is the displacement vector from X to X2. Okay. And that's the way you draw them. What I'm telling you is that as far as a model of what vector addition is, if you just string your straight path walks, and it don't even really have to be straight paths, it's just straight paths make a little bit more sense uh, to try to analyze. You could actually do, a number of infinitesimal, curved vectors, or vectors that are straight, but they're so short that their straightness is irrelevant because you move a half a centimeter and then there's another one a different direction. You move a half a centimeter, there's another one a different direction, and so on and so forth. So I'm just using the straight parts to make it a little more clear. In principle, you could have walked, like, let's say, from X, you could have done this and walked all the way to X2 along those black dots. And then the vector D1 would still be your displacement vector for that time interval. Okay. It's always a vector from where you were to where you are. So if you decide now to walk a little bit north, parallel to the road, I'm assuming north is up, then you could say, all right, well, this would be D2, and that puts you at, let's say, position X3. Again, that's just a position. So we've got another position. D2 is the displacement vector from X2 to X3. Now you might also decide to hang a right at this point and go stand by the corner, in which case you're now at position X4, and this vector is D3. Okay. Now that's all well and good, but what if you now decide to go south for an extended period of time? You could walk all the way down like this, and we'll end up now at X5. And this would be the displacement vector D4. So what I'm telling you is our model for addition of vectors is basically looking at individual displacement vectors and then drawing a vector from the tail of the first to the head of the last. So I want to point out, of course, that this end is the tail of vector D4, and this end is the head of vector D4. Oh, I don't know why I wrote a hat on that other one. That's kind of crazy. Okay, so just to make sure you know all the nomenclatures, so the vector is can be represented by an arrow. The tail of the arrow is the side with no head on it, and the side with the triangle or the partial triangle or whatever is the head side. And what I'm telling you is that the sum of any number of vectors can be accomplished by putting them head to tail, head to tail, head to tail, head to tail, until you've used them all up. And then you just draw a single vector from the head of the first to the tail of the last. So the thing you should learn is that if you connect, oops, the tail of one vector to your initial position and the head of that vector is at your final location, then the vector is a displacement. vector. In this case, of course, we use D1. So uh, this is one thing I want you to learn. Also, if you connect the tail of a displacement vector, that did not go so well. The tail of a displacement vector to the head of another displacement vector and repeat the process with all of the displacement vectors you have in any order. This is key right here, in any order. So I'm telling you to connect them head to tail, head to tail, head to tail, head to tail, and you can do it in any order. Then one single vector drawn from the tail of the first displacement vector to the head of the last displacement vector. Then one single vector drawn from the tail of the first displacement vector to the head of the last displacement vector is a vector that represents your total displacement I'm going to abbreviate that displacement vector, and it is the sum or resultant of all of the displacement vectors. I don't normally like writing this much, especially not in cursive, because I know a lot of students haven't been learning cursive lately, but it'd take too long for me to write it in regular script. And at least reading it to you, I think it's helpful for you to have. But let me repeat what I said. So I said the thing, but I should probably replace that with the things. The things you should learn is that if you connect the tail of one vector to your initial position, like we did with the blue D1 vector, putting the tail on the position X, And the head of the vector is at your final location, like we did with the head of D1 at x2. Then the vector is a displacement vector. So that was just a description of a displacement vector. So at any point, if you walk from some spot that you can imagine being marked on the ground or something to some other spot being marked on the ground, whether you make a straight path or not, doesn't matter. All that matters is your endpoint initially and your endpoint finally. If you draw a vector from the initial point to the final point, that vector will automatically be a displacement vector. So that's a big thing to know. Additionally, if you connect the tail of a displacement vector to the head of another displacement vector and repeat the process with all the displacement vectors you have in any order, then one single vector drawn from the tail of the first displacement vector to the head of the last displacement vector is a vector that represents your total displacement vector, and it is the sum or resultant of all of the displacement vectors. So in terms of the drawing we have right here, I have just four displacement vectors. In other words, I took a trip that could have been, an infinity of individual vectors, and I reduced it down to four, and pretending like they're all, very special or whatever. But if I want to know what the sum of D1 plus D2 plus D3 plus D4 is, all I have to do is now draw a vector from the very initial position, which was X, to the very final position, which was X5. So that's what I'm going to do, and I'm going to use a beautiful purple vector. So here's my beautiful purple vector. It's going to go right through the words, but that's okay. So I'm going to draw this vector right here, and this vector, as I said, ooh, I don't know what it did there, but I kind of like it. I will leave it. Okay. So this vector is S. Whoa, gotta take it off that thing. This vector is let's call it the R vector for resultant. You could have called it the S vector for sum, which is what I was doing, but this is the R vector, which is equal to D1 plus D2 plus D3 plus D4. And what we learned is, yeah, this is that vector, and that's always going to work. If you just put your vectors head to tail, head to tail, head to tail in any order, it'll always work. So, restating that any order part, I will say that R equals the resultant, also equals the sum of the vectors, and it is D1 plus D2 plus D3 plus D4, but you could choose to say it's D2 plus D4 plus D3 plus D1. It would still give you the same answer, because all you really have to do is imagine, let's start off with D2. So instead of doing D1 first, I would take D2, and I'm going to write these in, let's do them in sort of a reddish pink color or whatever. So this would be my D2. And now I would take my D4, which is this long sucker on the far right, and that goes all the way up to there. Now I'm going to take this long vector from here all the way back down to here, and that would be D4. And now I'm going to add to it D3. Well, D3 is this little vertical vector that seems to go about 2.5 squares. So I'm going to say 1, 2.5. There's my D3 vector. And now all I have to do is my D1 vector, and D2, D3. I wrote D3 backwards. Sorry about that. Let's take away that D3. I was reading D3 uh, as D2. That's why I drew it vertically. And D3 is actually this one that goes to the right, and it's one, two, three, four. It seems to be really close to like 4.8 cubes to the right. So I'm going to say, all right, now one, two, three, 4.8 to the right. And that is D3. And now if I just take D1 and add it, you'll see that it does turn out to be exactly the same spot. So notice I did it in an entirely different order and I still got the right answer. So that's a key part of what I was teaching you is the order that you add vectors in is irrelevant. Not only that, we're going to learn that you don't always have to do them head to tail like I did here. There's other ways as well. So uh, now you have some idea, at least some internal picture of what it means to add vectors. So vectors are just like little parts of a trip, and if you add them all together, you get the whole trip. And that's the way you want to look at it. So if I ask you, let's go to the next page, uh, draw, oops, a vector that is the sum or resultant of the two vectors A and B below. In other words, I'm not going to give you any numbers. I'm just going to draw two vectors. And I would ideally like you to draw two vectors just like I did in sort of the same orientation. And now I want you to draw on that diagram a vector that represents the sum of the two. So what I'm going to do is I'm going to say vector A is this guy, and vector B is this guy. For starters, can anybody tell me, are these vectors head to tail or tail to tail? Anyone? Anyone?
Is it head to tail?
Yes, they're head to tail. And the reason why is notice the head of vector A is at the tail of vector B. That's all that matters. If there's only two vectors, you only have one head to tail thing. If you have three vectors, there's two. If you have four vectors, there's three. It's always one less. So now, according to what we just learned, you're supposed to be able to draw a vector from the tail of the first to the head of the last, no matter what the order is. So, can anybody tell me uh, where your vector starts and where your vector ends? Or the more important thing is not whether or not I know whether you did it right. The more important thing is you to know whether you did it right. So I want you to think about the answer. I want you to write down an answer with your two vectors and then see if your two vectors are consistent with the answer that I get for my two vectors. Even though the two vectors are obviously different, in my case, my two vectors are slightly different from your two vectors, but that's okay. Okay. So I'm going to draw now the sum of the two vectors A plus B. And the way I do it is I start at the tail of A because that's the loose tail, and I draw it to the head of B because that's the loose head. Okay. So this vector is A plus B. Everybody see how you did that? Now, another thing to remember is since you learned that vectors have magnitude and direction, it's probably reasonable for you to think, well, if I don't change the magnitude or direction of the vector, then I can pretty much do anything I want to with it. And that's true, at least right now. When we start getting into electric field or into fields, vector fields, it turns out that those things have very specific vectors associated with very specific positions. So you just can't pick up a vector in a field and put it in another position because there's an entirely different vector associated with that particular point. So there's ways you got to deal with that. That it introduces like 9 different types of derivative and all sorts of crazy stuff like that. So the main thing to understand is until you get to the electric fields, which we cover in chapter 21 and 22, and further there out, magnetic fields as well. Until then, you're completely allowed to pick up a vector and move it anywhere you want. And as long as you don't stretch it, in other words, or compress it so that you don't change its magnitude, and as long as you don't tilt it one way or the other so that you don't change its direction, then that's perfectly fine. So what do I mean by that? Well, for instance, I can take vector B that you see right here, and I can actually uh, move that to the tail of A. So what I'm going to do is attempt to draw B at the tail of A instead. Now I saw that it went up 1, 2, 3, 4 squares and almost went a whole square in width. So I'm trying to use that to give me a guide of roughly what is a pretty good estimate. So it looks to me like this represents B if I were to pull it over to the left-hand side. Do y'all agree? Main thing is it should look parallel and it should look about the same length. Additionally, now that I've moved B, I want you to know you can also move A. And the reason why will become clear really soon. So now I need to draw A, and A evidently went upward about exactly a whole square, but it went to the right 1, 2, 3, 4, and maybe a tenth of a square. So this vector goes from here. Oops, let's try it again. From here to here. So that's our vector A when I move it. Now, again, I think you can see that now, in light of the red vector, this is also vector B plus A because notice B and A are in head to tail configuration as well, but B was the one we did first and A was the one we did second. So you can see that we ended up getting the exact same result for A plus B as we did for B plus A. So that's why commutative addition is commutative in vectors. You can just, see it, okay? Now that we have that, that also gives us an answer for how we go about adding vectors tail to tail. Now we can see how to add two vectors that are tail to, oh, I don't know why I crossed my L there. That was not intentional. Tail to tail, like that, okay? So now we've learned how to add two vectors when they're tail to tail and add two vectors when they're head to tail. Okay. Now, to be honest with you, another thing that is important to know is if you want to add A plus B plus C plus D, you can add A plus B first and then add C plus D together and then add the resultant of A plus B and C plus D, you can add those together. Alternatively, you can put my vector symbols on top of all this. Alternatively, you can also add A plus B plus C plus D that way. So it doesn't matter how you group them or the order. You can do it any way you want. Long as you count each vector exactly once and only once, then everything will work out. So you can add them, and I've now given you two prescriptive methods to add vectors. One in the case where two vectors are tail to tail, and one in the case where two vectors are head to tail. We just finished doing head to tail, and you can probably look at this and figure out how to do tail to tail. So now let's try a tail to tail example. So draw the resultant of D and C. So what I'm going to do is I'm going to say, there's my D vector, and there's my C vector. These vectors are tail to tail. So what I want you guys to do is try to guess. I mean, you saw something that I demonstrated with B plus A and A plus B with the tail to tail, or excuse me, with the head to tail configuration in the previous example at the top of this page. Now see if you can guess how you go about adding C and D when they're tail to tail. You go ahead and try it. I'm going to do it, and then we'll talk about the answer. Okay, hopefully y'all got that right. If you didn't, that's okay. You just got to correct it now. Let me explain what I did. What I generally do, and I try to explain this mechanically to my students. So I can imagine the vector C as if it's got a little loop on the end right there. And then I picture D like a little axle. So I can slide that vector up and down along D. That's all I'm doing when I drew the blue C up at the top. I just took the vector C and I slid it along D, making sure that I didn't stretch or compress D to change its length, and making sure that I didn't turn C to change its direction. So you'll notice, of course, C is essentially perfectly horizontal, just like the blue C up top is essentially perfectly horizontal. Similarly, the red D, which went up 1, 2, 3, 4 squares, and then went over 1, 2, 3.2 squares to the right, you can see that the blue D does the same thing. It goes to the right 1, 2, 3, and a little bit more, 0.2, and then it goes up 1, 2, 3, 4. So I'm going to say we have learned that to add two vectors in tail, there I go again, crossing my L's. I'm going to go ahead and put that word on the next line anyways. We have learned that to add two vectors in tail, whoa, Nelly, in tail to tail configuration, we complete, this is the wording that mathematicians and stuff, physicists and stuff use, we complete the parallelogram. So we have learned that to add two vectors in tail-to-tail configuration, we complete the parallelogram. Now, I didn't say it that way. I just said, imagine having a little ring on the end of C, and then you allow C to slide along D. And I didn't express it this way the last time, but let me do it now. Now you can imagine that little ring that I drew on C. Let's imagine now that it's actually on D instead of on C. And now I'm going to take D and slide it to the right along C, and that completes the parallelogram. In other words, the two red vectors just made an angle. But if you repeat the two red vectors in their different positions, then that completes a parallelogram. Notice the D on the left is parallel to the D on the right, and the C on the bottom is parallel to the C on the top. Opposite sides are parallel. That's the definition of a parallelogram. So if you complete the parallelogram when the two vectors are tail to tail, then all you have to do is complete the parallelogram and then draw the vector from the common tail to the common head. So complete the parallelogram, and the resultant runs from the common tail. No, everybody understand I'm saying common tail because it's the tail that's common to both C and D. I'm going to say this one a little differently. To where the two heads converge. Okay, so that's how you draw two vectors when they're tail to tail, how you draw the resultant or the sum of the two. Remember, resultant and sum are terms that just mean, hey, do the addition. So you got to be prepared to hear those words and know that that means add vectors. Now we need to go ahead. Actually, something's going on here. I want to make sure everything's okay. Let's go ahead and take our break. It's only 6:19. Let's be back at 6:28. So I'll give you about 9, 10 minutes. 6:29 will be fine. So be back at 6:29. I gotta go check. My wife is doing something, and now all of a sudden the refrigerator's ringing, and I'm thinking she might have left the door open. So, anyways, I will be back here in about 2 seconds, and I'm available. But you guys can take a break until 6:29. Almost back. Wait, folks, I'm gonna get a different drink. All right, I'm back, everybody. Still got about 5 minutes before we're supposed to get back. But now that I'm here, you're welcome to ask me any questions if you have any.
I have a question.
Yes, Ayana.
The extra credit that was under the first week, was that
Mhm.
due this past Monday or next Monday with the homework?
I, Whatever the due date is, let me double check it real quick. You
Okay.
said it was on this week's assignment?
No, like the first week. I
On
think it had said like January timing, but I'm not sure. I could be
I
tripping.
usually give a couple weeks to do them, but I didn't want to say that and you find out that I misremembered. So I'm checking right now. Uh,
Okay.
yes, I put January 26th and January 19th for the density of water one is January 19th, and the minimize the cylinder one is January 26th. So they were sort of arbitrary dates, but if you end up doing one of those ever, and it's after the due date, just let me know and I'll usually open it back up. And which actually I don't even require it to be done. Like you can turn it in late, and I don't take off points for it.
Okay, thank you.
No problem. I think the big deal is when we're doing that is January, or excuse me, July 28th is when all the homework has to be due, so that includes the extra credits too. I'll give you credit up until that day, basically, for any of the extra credits.
Okay.
The only reason why I even put dates on them is because Canvas, when you have a date on something, it puts a little reminder off on the right-hand side of the Canvas window to let you know that uh, there's something due on such and such a day. Without that reminder, you might not ever remember to do it. So I need to put a date on it, but I leave it where it's not to disappear or it doesn't allow you to no longer turn it in after a certain date. I always leave that part open so you can turn it in anytime. Okay.
Yeah, thank you.
You're welcome. Anybody else have any questions? I see Darius did chat me his first and last name. Y'all can go ahead and do that too. Anybody that hasn't done so already. We still got about 2 more minutes before we're supposed to start class back up. But like I said, we still have 2 more minutes to ask questions. Woodall, that's a cool ass name. I have some relatives that are Woodalls from the North Carolina area around Raleigh and Butner and that area. STEM. Ooh, Fleming's a famous last name too. Famous from a physics standpoint, that is. You might Google Wilhelmina Fleming and you'll find a really interesting, awesome woman. That's funny. Been hearing so much politics on the news earlier that when you said I'll look her up, I read it as I'll lock her up. Uh, yeah, they're called Pickering's harem is one of the phrases, or Pickering's computers. They're basically during World War One, a bunch of people were away. You know, the able-bodied men were away fighting war, so you only got the unable-bodied men and the very wealthy that were able to dodge the war. And those were all the grad students that people had, for instance, at Princeton and Harvard and those types of places. And Pickering was such a professor, and he was picking on one of his grad students one day and said, "My housekeeper could do a better job." And then, just to be the extra jerk that he could be, he brought his housekeeper in the next day. Her name was Wilhelmina Fleming. And she turned out to be not only, yes, better than that guy, but she ended up being friggin' brilliant. She could literally categorize a star looking at a photo of it within seconds. So she ended up cataloging 500,000 stars during her lifetime. But all those women were friggin' awesome. And most of them ended up getting degrees, in some cases PhDs, all sorts of cool stuff. All right, it's 7:28 now, 29 now, so I'm going to go ahead and get started. Does anybody have any questions on how we've done what we've done? Do y'all understand what we're doing here and think y'all could repeat it? I'm going to give you a try. So let's say I would like you to draw the sum of these two vectors. This is vector A and this is vector B. You draw it. I'm going to draw it in a second, and then you can compare your answer to my answer. I'm also going to have you oh, that's a really bad looking vector. I'm going to get rid of that vector. Okay, so now I've got two other vectors. This time the vectors are tail to tail, and I want you to add those two as well. This vector will be C, and this vector will be D. So you guys go ahead and see if you can add those vectors by just drawing a vector right on the diagram. Make sure it's connected. I want to see it touch, and you got to make sure you put the head on one end and make it clear. Like if you just draw a line connecting the two tips, that's not going to count. Okay. So you've got to decide exactly which direction it goes, as well as where it goes from and to. So the sum of A plus B is this vector right here. And the sum of C plus D is completing the parallelogram. This is not working as well as I hoped. I was trying to draw little dots to represent completing the parallelogram. So what's happened is now this vector is C, and this vector is D, and therefore the sum is not only from this corner to this, but you have to make sure I know that you're saying it points this direction. Did everybody understand that well enough to get right answers? Anybody need any help? Okay, now that we've learned how to add vectors when they're tail to tail and head to tail, I'm going to try to help you understand another thing, and that's multiplying scalars by vectors. So multiplication of scalars, or excuse me, of vectors scalars. Okay, so that's what we're working on now. So you might not necessarily think of what to do when you multiply a vector times a scalar, but here's an idea. Let's take vector A, which I'm going to say is a vector that goes from this dot, it'll go to the right 3 and then up 4. Actually, I ended up doing that one wrong. Nope, that was 3 and 3. And actually, I don't want that dot there anyway, so let's put this dot here. And actually, I want that a lot shorter. Let's do an easier one. I'm going to do two vectors, two dots by two, or two squares by two squares. So one vector right here, that's going to be A, is that little vector. And now I'm going to put another vector identical to it that is over 2 and up 2 as well. And that vector is also A. Now, if this was x plus x, what would you call that quantity? X plus x is called, you're doing algebra and you add x and x, what do you get? Anyone? X plus x is 2x. Just like that, A is a vector, but the symbol A acts just like a variable as well. So this is also called the vector 2A. So what we can glean from that is that if you add two vectors that have the same length and the same direction, you get a vector that is twice as long as the original one. And that evidently is the definition of 2 times A. So it seems to me that the vector 2A, is gotten by just taking the regular vector A and making it twice as long. What about if I did, let's say, I'm going to do vector B, like that, and now I'm going to subtract from it 3 vectors B. So actually, I don't want to do it that way. I think that would be a little bit problematic. So yeah, I'll just leave that one for right now, and I'll talk about addition in a second, or subtraction in a second. So that's our idea of the vector 2A. It turns out that in order to do a vector that is a multiple of a negative number, it's a little more complicated. But you might be able to guess by saying, what is the vector A? And then let's say, I don't want to do subtraction. I don't want to do that. No, that doesn't work too well. Oh, well, we'll stick with this right now. So when adding two vectors, or excuse me, when multiplying a vector, a vector by a scalar, oops, if the vector, or excuse me, if the scalar is positive and greater than 1, then the product is longer but parallel to the original vector. Okay, so if, for instance, if you want to multiply 3 times a vector, that's a positive quantity and it's greater than 1. The magnitude now is going to be 3 times as big as the other one. I didn't express that in that sentence. I said when multiplying a vector by a scalar, if the scalar is positive and greater than 1, then the product is longer but parallel to the original vector. The new length is the length of the original times the scalar. So for instance, let's call this vector, I'm trying to make it 1 square tall. Oops, that did not go well. Let's call this vector B. Now that means vector 2B would be that, oops, went a little far. Vector 2.5B would be that. I should call this examples as opposed to examples, Does that make sense to everyone? Y'all see that I've now increased the length by 2 in the case of 2B and by 2.5 in the case of 2.5B? Does that make sense? Now, here's another rule. When multiplying a vector by a positive scalar that is less than 1, the product is still parallel to the original vector. But the new vector, oops, is shorter or has a smaller magnitude. The length being the product of the scalar's length of the scalar and the vector's length. Okay. So for instance, let's say This is vector C. Therefore, this is vector 1/2 C. This is vector 1/3 C. Does that make sense to everyone? So whenever you multiply a scalar by a vector, all you're doing is either elongating it as long as it's positive. You're elongating it if the scalar is one bigger than one, and you're shortening it if the scalar is smaller than one. The new magnitude will be the scalar times the original magnitude in both cases. So I've got one more rule, and that's to deal with negative numbers. And you might have guessed that. For instance, if you assume, let's see, oops, I need to add some more space in here. Those are some problems for later. Okay, that should be pretty good there. I got plenty of those in there. All right, so now what about multiplying vectors by negative numbers? Or I'll say negative scalars. So when when multiplying a vector by a negative, scalar, you reverse the direction of the vector and then adjust the magnitude just like you did with positive scalars. Okay, so let me show you some examples. Let's say let's call this vector A. Vector negative A would be that. Vector negative 1.5a would be that. Notice that it's gotten 1.5 times as long. So instead of it being 2 blocks long, it's 3 blocks long. And because it's negative, it's obviously pointing in the backwards direction. And actually, I got a little rough with this drawing, so I need to be very precise here. Does that make sense to everyone? Everybody follow how we're going to treat vectors when we have to multiply them by scalars? Anybody have any questions on that? Okay, so let me draw a vector here, and you then draw something similar. I'm going to make it a little more complicated than the just vertical ones, because the vertical ones were just showing us exactly, so you can see exactly how long the length, how much the length changed. I'm going to just try a vector. Let's do a 45-degree vector that goes over 2 and up 2. So let's call this vector vector C. Okay. What I would like to see is draw negative C, 2C, negative 1/2 C. And let's say negative 3C. Okay, so you guys do it. I'm going to do it, and then we'll compare our results. So hopefully everybody got something equivalent to that. Anybody have any questions, or anybody not able to get those answers? Now, if you wanted to figure out why that is the way it is, why do you have to reverse the vector uh, as a result of multiplying by a negative number? All you have to do is think about this. Remember me telling you that those weird rules from algebra turn out to be something fundamental, important that defines something we call a vector space? Well, one of those rules is A plus the additive inverse of A is defined to be 0. So if we take vector A plus the additive inverse of A, we have to get 0. The only difference between this and what you learned in pre-algebra, algebra 1, and algebra 2 is I'm putting arrow symbols over them. And the reason I'm putting arrow symbols over them is because I'm saying, hey, these things are vectors, not numbers. You would have normally said lowercase a plus the negative of lowercase a, and they'd put it in parentheses, is equal to 0, and that would be right. Well, if you think about it this way, that a plus the opposite of a, or a plus the negative of a, means that I need to take a vector. Let's say if this were a, for instance, I need to add a vector to that that makes this vector turn into just a dot. In other words, I need to erase the whole magnitude of A except for that leftmost infinitesimal sliver of blue left on the vector. Well, the only way you could do that is add to it a vector that is equally long, but in the opposite direction. So you see that obviously in order for A to cancel out, uh, to be canceled out by negative A must have actually the opposite direction as positive A. So hopefully that makes it make more sense as to why it's positive and negative. The other way of doing it would have required me to first introduce subtraction, but that's what I'm getting ready to do now. And I've got to do subtraction, and I've got to do subtraction just like I did with addition. I did addition with tail to tail vectors, and then I did addition with, or excuse me, I did addition with head to tail vectors, and then I did addition with tail to tail vectors. I'm going to do the same thing now. I've got to teach you how to subtract vectors, and I'm going to teach you how to subtract them graphically when they're tail to tail and when they're head to tail. So In this way, in this case, it actually turns out to be easier to do the tail-to-tail ones when you're subtracting, whereas when you're adding, it's easier to do the head-to-tail ones. So now we address vector subtraction. Okay, what we know is from algebra, A minus B is defined to be A plus the opposite of B. That's the way we learned how to add and subtract signed numbers when we were doing pre-algebra and algebra 1 and algebra 2. We said A minus B is defined to be the sum of A and the negative of B. So in vector, oops, in vector algebra, A minus B is defined to be A plus the opposite of B. And remember, the opposite just means multiply it by -1, which we learned means just reverse the vector. Okay, so I'm first going to talk about head to tail, and you're going to see that they're not that convenient. So if I take two vectors and put them head to tail, let's say I do vector A like this, and I do vector B like this, and I want to know A minus B equals question mark. So what do? The first thing I do is I combine, or I change B, the subtrahend, if I remember correctly, with the proper wording of what parts of the subtraction are what. I take the second thing in the subtraction and I reverse the direction. So the way I'm going to do that is I'm just going to draw it as blue right next to B, like this, and put the head there, and I'm going to label it negative B. And that, of course, just means the blue vector that you see, not the red vector. But now you see that vector is head to head, which doesn't help us at all. Remember, our vectors, we learn to add them when they're head to tail or when they're tail to tail. Right now, they're head to head, so that doesn't help me at all. But I can always use my little ring thing. So if we imagine a little ring being on the end of the vector, then that little ring and that vector can slide along until the B vector is in fact at the far end, and it'll be loaded up head to tail. So what I'm now going to do is draw the vector negative B right there. So that's what negative B is. Now you have negative B and A are, this is a question for you guys. So, just blurt out the answer. Is A and the blue negative B that I just drew, are they in head to tail or tail to tail configuration? I'm asking whether this blue vector right here and this red vector right here, are they head to tail or tail to tail? Okay, so what we see is the head of this blue vector is on the tail of this red vector, so they are now head to tail. And the way we add vectors that are head to tail is we draw from the tail of the first to the head of the last. And that means our vector a minus b is this vector. So that's how you end up doing a minus b. By the way, I slid b along, or I slid the vector negative b, I slid it along a. You can also now imagine a as if it's got the little ring, and then we slide a along b like that. And when I do that, then I get a completed parallelogram. So in that case, you can sort of look at it as completing the parallelogram, but you don't really have to go that extra step every time. Sometimes you do, sometimes you don't. So I just wanted to point that out. So if the vectors are tail to tail, excuse me, if the two vectors are head to tail, you first reverse the vector that is being subtracted. The one after the minus sign. So you first reverse the vector that is being subtracted, and then you move one or both vectors so that they are in head to tail or tail. Oh, there I go again, crossing my T, crossing my L, or tail to tail, and then add them like we previously learned. So that's how we did that. If two vectors are head to tail, you first reverse the vector that is being subtracted, the one after the minus sign, in other words, and then you move one or both vectors so that they are in head to tail or tail to tail, and then add them like we previously learned. So we've already learned how to add two vectors when they're head to tail. We've learned how to add two vectors when they're tail to tail. So when I moved the negative b to the far left-hand side, those two vectors were already head to tail. So I could just draw from the tail to the head and I would get the right answer. But if you didn't see that, you could also pull vector A up to the top, and then you'd have the two vectors tail to tail, and you'd know to just complete the parallelogram. Now we're going to do tail to tail. So we're going to have two vectors that are tail to tail. I'm going to draw them blue this time. So this vector is going to be A, and this vector is going to be B. And let's say this time I want to know what is B minus A equals question mark. Okay, so the same sort of process happens again. I first am going to reverse the direction of the vector that's being subtracted. The vector that's being subtracted is the vector after the minus sign. The vector after the minus sign is vector A. So I'm going to reverse the direction of vector A by just drawing a red vector right next to it, dotted, and putting the head at the opposite end. So we now see this red dashed vector is in fact the vector negative A. Uh, Once I've done that, you can see that now vector negative A's head is touching vector B's tail. So they're already head to tail. Therefore, we know the answer of B minus A is this vector. Now, alternatively, if it didn't necessarily work out like that, I could have went ahead and imagined moving the B. So we can picture the little ring on the vector B and then sliding it along vector A like this and continuing to do it until I got to here, which would be, of course, it's going to go over 4 and down 1, which would be like that. So now I could go ahead and write this vector as down 1 and over 4. So it's 1, 2, 3, 4. Oops, that was supposed to be red. Like that. And then I could move the vector negative A. And this time I'm imagining that it has a little ring here or a ring here, either one. And I'm just sliding, 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 sliding all the way until I get back exactly what I had before. So there's my vector negative A. Okay. So again, you can see in that case, we've completed the parallelogram, but we didn't necessarily need to because we'd already done it before. So now you've seen exactly how we can add two vectors when they're head to tail. We can add two vectors when they're tail to tail. We can subtract two vectors when they're head to tail, and we can subtract two vectors when they're tail to tail. Anybody have any questions on that? Notice how the tail to tail was a little easier for subtraction and the head to tail was a little easier for addition. Okay, that'll help you remember which one's which if you have any difficulties forgetting. Hopefully, the whole argument of how I made all this, it make so much sense that you couldn't come up with a way to do it incorrectly. But in case you haven't, then you can always refer back to this video or to your textbook or to my notes or all of the above. So definitely check those out. Does anybody have any questions on how to deal with vectors graphically, adding them head to tail, tail to tail, subtracting them, head to tail, tail to tail? Does anybody have any questions on that? Okay. So that looks like we're in a pretty good spot where we are on that one. I didn't actually write out the paragraph here, but it's essentially the same paragraph. If the two vectors are, in this case, I'd say if the two vectors are tail to tail, you first reverse the vector that is being subtracted, the one after the minus sign, and then you move one or both vectors so that they are head to tail or tail to tail, and then add them like we previously learned. So it's the exact same process, only now they're not initially head to tail, they're tail to tail. Okay. All right. So now that you know how to add them graphically, I will tell you one of the most awesome things you can have, and your instructors might not have told you this yet if you're in engineering, but AutoCAD gives students a free license while they're in college. So you can get the whole Autodesk suite of AutoCAD from AutoCAD for free. All you have to do is apply for it. I think you can just go to their website. That's the way I did it personally. But you go to their website and you do it, and they'll let you download just AutoCAD or AutoCAD with the Autodesk suite. Which includes a lot of stuff for us builders and engineers. When I used to work in engineering, that's the kind of stuff that we have to use and stuff like that. But it is completely free, and I think they allow you 4 years to do it. So if you are actually working on your bachelor's or even your master's, you're going to get at least 4 years out of it. If this is your first or second year, might as well take it now. And you can use AutoCAD to draw vectors, and it will automatically give you exactly the right answers. So it's a really wonderful tool to play with in terms of adding vectors. And it always gives you a litany of correct answers because all you have to do is draw the vector. That's pretty easy in AutoCAD to actually draw a vector of a certain length at a certain direction. It's just a keystroke commands that you can type in to make it. And then at the tail of that, or at the head of that vector, you can put another vector. And at the head of that vector, you can put another vector and then draw them all. And then you can just click on the vector and it'll tell you what its direction is, what its magnitude is. And that vector could be the resultant, for instance. So do check that out. If you haven't already gotten a free copy of AutoCAD to use while you're in your engineering program, then by all means, get it now. If you think you're going to take more than 4 more years, you might want to wait a year. If you don't think you're going to take more than 4 years, then go ahead and do it now. So now that we have that, I'm going to go ahead and start to talk about why or how we add vectors when we actually want to do it algebraically. In other words, we want to do it numerically, not graphically. Now, to be honest with you, if you drew these things with, a lot of care and precision using, protractors and compasses and stuff like that to try to make sure you can get exactly the right lengths and you use a really good scale and you use graph paper and that kind of stuff, if you really, really do it precisely, you can get really good results that will only differ from the mathematically calculated ones, which are the correct ones. They'll only differ by a couple percent. In fact, I've never had it go over like 7%. So it's really pretty straightforward to do. I'm going to demonstrate that in a second doing them graphically, but I'm also going to work out the algebra way as well. With that being said, I got to express to you how we actually label vectors and tell you about them. So I'm going to skip a couple pages to this page right here. And what I've written in blue is an alternative way of indicating the vector. So I'm asking, what is the resultant of the following vectors? Vector A is 10.00 newtons at compass heading of 36.87 degrees. Vector B is 7.07 newtons at 45 degrees west of north. Vector C is 8 newtons at 30 degrees south of west. And vector D as in dog is 10.00 newtons at 323.13 degrees. Now, you will see in your module, for instance, that I've got a link to the world's greatest vector problem. And the reason why I even suggested that as the world's greatest vector problem is basically a homage to the movie Elf. I'm big on kids' movies and big on movies from my children's childhood as well as from my adulthood. So I'm referring to the world's greatest cup of coffee, which, Elf celebrates, and it's just a crappy cup of coffee. But in this case, I'm actually meaning a little bit in that specifically that world's best vector addition problem is really a problem where I took the time to make sure I indicated every possible way I can label a vector, and I did each vector differently so that you would see all the different ways. I've done the same thing here a little by cheating. So for instance, vector A is at the compass heading of 36.87. In order to understand that, what you have to do is look down at the coordinate system I have drawn and realize that the x-axis is normally what we call east, and that's also what we call 90-degree heading. Okay, so that's a 90-degree compass heading. Similarly, the y-axis is due north, and we would call that a 0-degree compass heading. So when you're headed due north, the compass heading is 0 degrees. The negative x direction, of course, is the west, and that's a 270-degree compass direction. And the negative y is due south, and that's a 180-degree compass direction. Now, in addition to all that, we could also talk about the mathematical angles. And with that in mind, then I would say that 0 degrees actually becomes at 90.00 degrees. What I mean by that is if I give you a vector like I did in D, it says 10.00 newtons at 323.13 degrees. If I ever say a vector is just at some angle, and I don't even have to use the at symbol, I'll just say at such and such an angle, then what I'm referring to is exactly what you learned in trig. Namely, a positive angle is measured counterclockwise from the positive x-axis towards the positive y-axis. That's why if I try to imagine taking an angle from the positive x-axis to the positive y-axis, I see that that angle is 90 degrees. That's why I put that here. Similarly, if the vector is right along this, that angle is 0 degrees. So I'm going to write at 0 degrees. Similarly, if I were to say exactly what due south is, then that could be done two ways. Either it's 270 degrees or it's at negative 90 degrees, because that's the other thing. If you go, instead of going counterclockwise from the positive x-axis, if you go clockwise, then that angle is considered negative, and that's why I got a negative 90 for south. Finally, west would also be at 180 degrees. Of course, you could also say it's at negative 180 degrees as well, and that would work too. Okay, so those are sort of the ways that you could express a vector's direction in terms of just pure mathematics. So when we say a vector is at 30 degrees, that means 30 degrees north of east. If we say a vector is at 90 degrees, we mean that's north. If we say a vector is at 45 degrees west of north, then that angle is 135 degrees, because you've got to go 90 degrees to get to north, and then you go another 45 degrees. 90 plus 45 is 135. So that's where all these numbers are coming from. So you can look, for instance, at vector A, which I said was a compass heading of 36.87. That means this angle right here is 36.87 degrees. But I also said it's at 53.13, so that means this angle right here is 53.13 degrees. Now, how do we draw the next vector? So the way we would start adding these graphically is we would start at the origin, and we take the first vector and we put the tail right at the origin. And then we use a protractor to measure the individual angles. So since this one said compass heading 36.87, what I would do is take a compass and mark 36.87 degrees. You might say, well, how do you do that, Mr. Younger? And I would tell you, this is how we do that as soon as I find my protractor. So when you look at a protractor, let me stop sharing the screen for a second and turn it back to this. So when you look at a protractor, what you have to realize is at one side and the other are 0 and 180 degrees. Okay. There should be a somewhere on it, some reference to a straight line that connects the 0 on this side to the 180 on this side. And dead center on that line is what's supposed to be the apex of the actual angle. So when you go to measure an angle, you have to put the vertex of the angle in the center of this little hole. For this protractor, they actually have a hole. Sometimes they don't even have a hole. They just have it run out to the flat end and you use the flat edge. Sometimes they don't have a flat edge near it either. They just have sort of two crosshairs and you line them up under it. The main thing is you need to make sure the vertex of your angle is on the line that connects the 0 degrees and the 180 degrees. And then whatever you're measuring it from should have the 0 line lying right across that line. So for instance, if we're using the typical notation that we use in trigonometry, where the angle is measured positive counterclockwise from the positive x-axis, then what I'm going to do is I'm going to take this 0 degrees right here and this line, I'm going to lay that right along the x-axis, and the coordinate origin is going to be in the center of that circle. And when I go to put an angle of, let's say, 53.13, then I go up here to the angle 50, and then I see that I have individual angles between 50 and 60. I've got 10 individual spaces between the 50 and 60. So each of those is a single degree. So I can go over 3, and then I can estimate about a tenth of another degree, and I'd put a little mark right here. Then I just draw a line connecting the origin. You can take away the protractor now, but you're going to connect the origin to that little dot, and you just draw a line. You just draw it that long no matter what, and then you adjust the scale to whatever scale you decided on the paper you're drawing. So your scale might be 1 Newton is equal to, a tenth of an inch or a millimeter or something like that. I've been using mostly squares on this diagram, but that's the way you do it. You have to use the center of the protractor. You have to find the 0, 180 line. That 0 part has to be lined up on the angle, on the axis that you're measuring the angle from. Then you mark the angle, and then you draw the line through it, and then you adjust the length of that line, but still parallel to that line that you initially drew so that it has the right magnitude. So in doing that, that's what I've done here on the diagram I'm showing you. So I'm going to go back and share the iPad screen again so we can get back to this. It should pop up any second now. There you go. Okay, so when I said 10 newtons at a compass heading of 36.87, as I said, I could actually measure downward to 36.87 degrees. Okay, again, in this case, what I would do is put the 0 line along the y-axis, and I'd put the center of the arc, which is the center of that line from 0 to 180, I'd put the center of that right at the origin. So the center of the origin, the center of the circle should be right in the origin. So the origin's right in the center of the circle. And then I'd measure down 36.87 degrees, make a mark, draw it. And then what I do is measure out the length to be 10. In this case, what I actually did was I was using the fact that it's a 3, 4, 5 triangle, and I basically went to the right 1, 2, 3, 4, 5, 6, and then I went up 8. And by doing that, that made the co-angle, or the one that I didn't draw, that makes that 53.13 degrees. So hopefully that makes a little bit of sense. But that's how I did that first one. Now, at the head of that vector, I have to draw the second vector. So what you'd normally do is draw another y-axis and draw another x-axis. And you really want to be careful and draw this exactly correctly. For instance, what I'd normally do is I would use my tool that allows me to draw figures very, very correctly. And it also normally makes sure that I'm square. So now this is my x-axis, and this is my y-axis. And the second vector, vector B, is supposed to be at 45 degrees west of north. Well, 45 degrees west of north is this angle right here. And it is to 2 decimal places, but I need to reserve space, so I'm not doing that. I will call this vector A right here, and I will call this vector B right here. Now, in this case, this was an actual 45-degree vector. So what I decided to do was I would go up exactly a certain number of squares, 1, 2, 3, 4, 5 squares, and then I'd go to the left 5 squares, 1, 2, 3, 4, 5 squares. And therefore, I knew that the actual magnitude would be 5 squared plus 5 squared, take the square root. Well, that's the square root of 50, which is about 7.07. That's where I got that magnitude. But hopefully you can see how that works. Now, again, I have to do vector C. And in order to do vector C, I need another coordinate system at the head of the last vector. So again, this is my x-axis and this is my y-axis. And this time I'm told to do it 30 degrees south of west. So this is south of west by 30 degrees. In this case, what I discovered was, of course, one side should be the square root of 3, and then the other side should be 1. So what I did is I went to the left 4 times the square root of 3, which gave me like 6.93. And then I went down 4. And that allowed me to get exactly the 30 degree that I wanted, fairly closely anyways. I say exactly, but fairly closely. But the main thing is all you do, it's a lot easier to do it when you're not doing it on an iPad. All you would do is just draw your axes, make sure your new x-axis and your new y-axis are actually parallel to the old x-axis and the old y-axis, and then measure the angle with the protractor, mark the dot so that you can draw from the origin of that coordinate system through that dot, and then shrink the size to the appropriate size of whatever scale you use. Again, you always try to use a scale where you can almost, where you can take up most of the page, if not all of the page, because the bigger it is, the less likely you are to make errors, and the smaller the errors will be, so you'll get better results. Now that I've done that, I've done vector C. I'm going to go ahead and label that vector C. And then I got to do vector D, which again requires me to draw a coordinate system. So here's my coordinate x-axis. Here's my y-axis. Let's say this is my x-axis and this is my y-axis. Now in this case, it was 323.13 degrees, which I happen to recognize as 53.13 degrees, or excuse me, 36.87 degrees shy of 360. So since it was 36.87 degrees shy of 360, that meant this angle right here is 36.87 degrees. Okay, so that's how I drew that one. And of course, that vector is vector D. So now that I've completed it, you can see that the end of vector D is right here at that little spot. So that actually is a little inconvenient because I drew my arrow pointing to the angle. I drew that right in the way. So I'm going to try to move that now, just to make life a little easier. So what I'm going to do now is say that this angle does this. And that looks almost perfect. Again, of course, we would want to ideally get rid of this stuff, but we can't always do exactly the way we want it, but close enough. So that's in there. This here does that. And I actually had a little bit right there is about where the end of the vector was. Okay, so that's the end of the vector. Now, the resultant is just a vector from the tail of the first to the head of the last, just like we learned earlier. So what I'm going to do is I'm going to change my color to purple, and I'm going to draw the resultant vector. And here it is. Oops, that did not come out well. Oh, well, let's see. This vector, this tail should be at the origin, so I move that. And this head should be right there, so I move that. So what I just drew there is the vector R, which equals A plus B plus C plus D. And I can use my protractor to estimate the angle. I'm literally just going to lay my protractor with the coordinate origin inside the center of the circle that is the center of the arc for the protractor. And I'm laying the 0, 180 line along the positive x-axis. And now I'm trying to read exactly what angle this purple vector goes through. And it appears to me that this purple vector goes through the angle 50, looks like 56.0 degrees on the money. So I'm going to now say that this angle measured 56.0 degrees. Now, additionally, I need to get an idea of how big that is, and the units I used were actually in units of blocks. So I could either take the square of 2, which is how many blocks went to the right, and the square of it looks like a little bit bigger than a half plus a whole plus a whole plus a little bit bigger than a half. That's obviously not what we want to do. So what I'm going to do is I'm going to use my scale to measure the actual length of this purple vector, and I'm going to do it in kind of a large area so I can see. So when I do it at this size, the vector appears to have a length, and I'm sorry, my protractor is only marked in inches, so I'm going to have to use that measurement right now, but I'm just doing it long enough to figure out exactly how many cubes this is. This looks to me to be 3, and that's 3 1/4. That's 3 1/2. So these are 16ths. So 1, 2, 3, 4, 5. So I'm looking at 3 5/16. So the length is 3 5/16, and now I'm going to try to figure out what that is in blocks. So I'm now measuring 3 5/16 on the line below it. It goes from here to 1, 2, 3, 4 to here. That appears to be 1, 2, 3, and then some fraction of a whole block. And now I'm going to use a ruler to determine the size of that fraction of the block. On this scale, I'm going to try to, now I have a ruler that actually has centimeters, so that's kind of helpful. On this scale, the individual squares are 2 centimeters. That's really helpful because this purple dot is 14.5. So this one is 14.5 out of, and I said 14.5 is 1.45 centimeters or 14.5 millimeters. So this would be 14.5 out of 20 millimeters. So if I take 14.5 and divide it by 20, I get 0.725. So 1, 2, 3, my length is evidently is 3.725 newtons. Okay. And as I said, I measured that to be 56 degrees. So I'm going to make that a little bigger so y'all can see it when I expand out. So that's the measurement that I got for the resultant of this by doing it graphically. So I literally did it graphically, and I did it graphically on an electronic device, which makes it even harder. Yet I still suspect I'll have very good results. So let me compare to the actual algebraic sum of the four vectors. So in order to do that, I need to teach you guys how to do that. So what we're going to do is we have to take each vector and imagine it casts a shadow on the x-axis, and then imagine it casts a shadow on a plane parallel to the y-axis. The shadow it casts on the x-axis is called the x component. The shadow it casts on the plane parallel to the y-axis is called the y component. And in order to figure out which direction those components point, you have to start at one end of the vector. Usually you start at the tail of the vector and then move only parallel to x and only parallel to y until you get to the head end of the vector. And the directions you move, if they're to the right and up, then they're positive. If they're to the right and down, then the right one is a positive x coordinate and the down one is a negative y coordinate component. So if I look at this now, you can see that for vector A, its shadow is basically this. That's the x component. And notice I started at the tail. I moved parallel to the x-axis and I had to go to the right. So the x-axis, the x component of A is positive. Then I moved from there parallel to the y-axis up here. And that you see is pointing up. So that's also a positive component. So I can now see that A has positive X and Y components. When I look at B, I will start from the tail again. I'm going to go up here, and the Y component is obviously positive. The X component, on the other hand, is obviously negative. When I do C, again, I start from the tail. I can see the X component is negative. I can see the Y component is also negative. And then finally, to do the D, I can see that the Y component, which goes from here to roughly here, the Y component is negative, and I also see that the X component is positive. And I use these angles to actually decide how to calculate these. Okay. So I'm going to go to the next page, and what you'll see is I have I have a positive X component right here and a positive Y component right here. That's why I'm drawing them red. Okay. And this angle we found was 53.13, or this angle we found was 36.87. Either one's fine, but I just wanted to point that out that you can use either one of them. I'm going to erase that 36.87 just because I don't need it, and I'm going to use 53.13, but you can feel free to use that. Now, what I recommend you guys doing, at least till you get more comfortable, is immediately write out the sine and cosine. So I'm going to write the sine of 53.13, and I'm going to use my mnemonic, and my mnemonic is some old horse came a hopping through our alley. That's also the same thing as SOHCAHTOA, which other people use. But sine is opposite over hypotenuse. The opposite of the 53.13 degree angle is the side that's not touching the angle. So this side right here we call the adjacent angle because it's touching the angle. This side right here we call the opposite because it's not touching the angle. And this opposite, of course, is the y component. So I'm going to write a sub y over the hypotenuse. Now the hypotenuse, remember, is just the magnitude of A. So in this case, the magnitude of A was 10. So I'm going to write it as 10.00 newtons. Now I'm going to write cosine 53.13. Remember, this is ka or kama hopping. So it's cosine equals adjacent over hypotenuse. And as we said, adjacent is this side, which is the x component, and the hypotenuse is the 10 newtons again. So I'm going to go ahead and say it's a sub x over 10.00 newtons. By doing that, I can now compute that the y component is just 10 times the sine of 53.13, and the x component is 10 times the cosine of 53.13, but I need to put the sign on them manually. So you literally have to force the sign to be on there. So what I can immediately say is a sub x is equal to 10.00 newtons times the cosine 53.13 degrees. And that gives me 6.0 newtons. Similarly, a sub y, again, I force the positive, so it's 10.00 newtons times the sine of 53.13 degrees. And that too is positive. And in this case, it turns out to be 8.00 newtons. Okay. Now I've got to do the same thing for the b vector. So the b vector has a positive y component. I'm drawing these fat on purpose. So this one's positive, but this x component is negative. Now, in addition to that, this one was 45 degrees west of north. So that means this angle is 45.00 degrees. I know I wrote that with such fat writing that you can't really see the two zeros. So it might be best if I just do it with a less fat writing. Okay, so now I'm going to compute that. And again, I recommend you just take the time to write out the trig, both the sine and the cosine function. So the sine of 45 degrees is equal to opposite over hypotenuse. Well, in this case, the opposite is this side over here, and that happens to be the x component. So I'm going to say this is b sub x. And it's divided by the hypotenuse, and the hypotenuse, of course, was the 7.07. So I'm going to write 7.07 newtons there. I'm also going to write cosine 45 degrees. Notice I'm just writing cosine 45 without the decimal places just to save some room. Cosine is adjacent over hypotenuse. Adjacent is the angle that's actually touching, or excuse me, it's the side that's actually touching the angle. So this is our adjacent, this is our hypotenuse. The adjacent, of course, is the y component. So that's b sub y over 7.07 newtons. And that gives us b sub x is equal to I'm going to leave off the units just to save room. 7.07 times the sine of 45.00 degrees. And I have to remember that it has to be negative, so I'll force the negative sign there. And now I'm going to type 7.07 times the sine of 45. And that gives me negative 5.00. Similarly, by is actually positive, and that's going to be 7.07 times cosine 45.00 degrees. This one gives you, of course, a positive, but it still turns out to be 5.00 newtons, which I'll put there. Now I'm going to do the same thing with vector C. Probably wouldn't hurt for me to label these vectors. I think you all remember how I did them, but anyways, both of these are negatives. So I'm going to now draw the components for vector C. Oops, a little jacked up there. So that x component is negative, and that y component right here is also negative. Don't worry about me not drawing it exactly the right length and all that stuff. That doesn't matter too terribly much. This angle, by the way, is 30.00 degrees. And this length, of course, was 8 newtons. So this is vector C. And the magnitude of C, which you can write this way or this way, it's equal to 8.00 newtons. So you can put it in absolute value bars with the vector symbol over it, or you can just write the symbol without the vector symbol above it, and everybody understands that that's just the magnitude. Again, I'm going to write down both trig functions. So I'm going to say sine of 30 degrees is equal to opposite over hypotenuse. And the opposite in this case is C sub y, and the hypotenuse is 8.00 newtons. Cosine 30 degrees is equal to adjacent, which is the C sub x, over the hypotenuse, which is 8.00 newtons again there. So that gives me C sub x is equal to, again, I got to force that negative. It's going to be 8.00 times cosine 30 degrees, which equals negative 8 times cosine 30, which equals 6.93 newtons. And C sub y is equal to negative 8.00 sine 30 degrees, which in this case, 8 times sine 30 is 4. So that's negative 4.00 newtons. And we've got that one as well. Now all I've got to do is the last components for for vector D. And obviously the y component is negative, so I'll draw it. Oops. So I'll draw it right here. And I'll put a negative sign there. But the x component is actually positive, so I'll put it right here like that. And what I got to remember is that this angle right here is 53.13 degrees. Okay. So with that in mind, I can go ahead and write the sine of 53.13 degrees is equal to opposite over hypotenuse. The opposite of the 53.13 is the positive x component. So that's going to be d sub x over the magnitude. and the magnitude of that was also 10.00 newtons. And the cosine of 53.13 degrees, we're almost out of time, is equal to, in this case, we're going to get ultimately a negative. I know I didn't normally put it there, but for some reason I put the plus last time. But in this case, it's adjacent over hypotenuse, and the adjacent side is the y component. So I'm going to say d sub y over 10.00 newtons, again, because that's the magnitude. So now I can say d sub x is equal to positive 10.00 times the sine of 53.13. And that's going to give me positive 8.00. Similarly, d sub y is going to be the negative of 10.00 times the cosine of 53.13 degrees. And that's going to give me negative 6.00 newtons. Okay. Now that I have all these numbers, I can go ahead and do this. And some people will actually tell you to make a table. That's certainly fine. Calculus-based physics students generally don't make tables, but make them for as long as you need to until you get the hang of it, and then throw them away. But what I'm going to do is I'm going to say x component, y component, and vector A, we found the x component was positive 6.00 newtons, and the y component was positive 8.00 newtons. For vector B, it was negative 5 and positive 5. For C, it was negative 6.93 and negative 4. And for vector D, it was positive 8.00 newtons and negative 6.00 newtons. All you have to do is now you have like components, so you can add like components. That means the resultant vector R has an x component that is 6 minus 5 minus 6.93 plus 8. That gives me 2.07 newtons positive. And then 8 plus 5 minus 4 minus 6 gives me 3.00 newtons, and that's also positive. Now, how do we make this into a vector? Well, now we draw our axes again. I'm going to draw an x-axis and a y-axis. There's my x-axis. Oops. There's my x-axis. There's my y-axis. Okay. And what we have is a vector that has an x component of 2.07, which should be really, really small. I'm going to say it's roughly there. And then I have a y component that is actually I made that a little longer than it should be. It should be less than 1/10. So let me fix this a little better. I would say this is roughly less than 1/10. And even that's a little bit long, but that's roughly good enough. So we'll say so that's that one. Now the 3 one will point up, and it will be 3 squares long, just like that, and that's 3.00 newtons. So our actual resultant is this vector right here. And and it has this angle phi. R is equal to the square root of 2.07 newtons squared plus 3.00 newtons squared. Take the square root. That's the square root of 13.28. Now, when we added 2.07, when I squared that, I got 4.2849. I only had 3 sig figs, so that's only good to two decimal places. And the 3 becomes 9, and that's only good to 2 decimal places. So really, this 4 and this 9 are not real sig figs, but I did manage to make it now all of a sudden that I have 4 sig figs. So now I'm going to take the square root of the 13.429 or excuse me, 13.2849. I'm going to take the square root of that, and that gives me 3.645 newtons. It's actually 6.44845, but that's roughly the magnitude. The magnitude I got when I measured it on the graph was 3.725 newtons. So you can tell that's pretty close. That's not a lot of percent error. 3.725 minus 3.645 is 0.08. If I divide that by 3.645, because that's the correct one, that gives me 2.1, or I might as well say 2.2% error. Not bad. Now, the phi is the inverse tangent of 3.00 divided by 2.07. So if I take inverse tangent parentheses 3 divided by 2.07 in parentheses, I get 55.39. That's one extra sig fig, by the way, or one extra digit. That's 39 degrees. Now, graphically, I got, what was that angle? 56.0 degrees. So 56 minus 55.39 is equal to 0.61. If I divide that by 55.39, that gives me 1.1% error. And that's how you add vectors. It's now 3:55. I actually went over by 5 minutes. Y'all are always welcome to leave at any time. If I run over, it's okay. It'll still be recorded. You're free to go. Make sure you chat me your first and last name if you haven't already. Include that you're from the asynchronous class if you are. But other than that, you are free to go. I'm going to wait for the last person to leave before I leave, but I'm here to answer questions if you have any. Uh, Feel free and have a good lab whenever you do your lab.
I have a question about my proctor.
Yes.
I think my proctor emailed you.
Yeah, they did. I haven't got the application together, and I think you even replied and asked me if I'd sent it. Is that correct, Kaylee?
Yes.
Yeah. I'll get it to him. She's got plenty, or she or he's got plenty of time, but I'll probably do it tonight. If not, I'll do it tomorrow. But you're doing good by reminding me because there's a good chance I'll forget. You know that.
Yeah. I was just more curious because I know it said it had to be like a week in advance, so I wasn't sure if it was gonna be too
No.
late.
You've met your responsibilities. All the rest is up to me now.
Okay, perfect. Thank you so
I
much.
know. Screw up. You're welcome, Kaylee. Anyone else? Well, thanks for coming, everyone. we'll talk about unit vectors next time, but we got through quite a bit today. That's a lot of stuff. And next time we'll do unit vectors, and then I'll do projectile motion. I'll derive some nice results, and you'll have a pretty good understanding of chapter 3, and we can move on to chapter 4, which is where we finally get the dynamics. Right, Michael, you still here? Or Adrian, you still here?
Yeah, although I have a question mainly because I'm behind one unit. It's just a question about the kinematics.
Okay, what's that?
It's a constant acceleration question because I'm immediately having a hard time trying to figure out
Right.
how you find a constant acceleration.
So yeah, that's a common problem students don't get. But for instance, as an everyday life example, if you wish to throw a ball upward, okay, let's ignore air resistance. If you're throwing a sort of heavy ball, air resistance shouldn't be a problem unless the wind is really strong anyways. So we'll just go on that assumption. But if you throw a ball upwards, while your hand is touching it, your hand is applying a force to it. Newton's second law tells us that the acceleration is not going to be constant unless the force happens to be a constant. But it's not a particular force, it's the sum of all the forces. So when your hand is touching it, it's got whatever force the hand is putting on it minus the force of gravity, which points downward. But the instant it leaves your hand, then the only force acting on it is the force of gravity, which turns out to just be m times g. So if the mass was 1 kilogram, for instance, you take 1 kilogram and multiply it by 9.80 meters per second every second, and you get 1 Newton, or excuse me, 9.80 newtons. That is the actual weight of the ball. So as soon as it leaves your hand, the whole force acting on it is exactly 9.80 newtons. So the acceleration is going to be a constant for all the time that your hand is not touching it. So as soon as it leaves your hand, it's going to go up, accelerating at a constant 9.8 downward, 9.8 downward, 9.8 downward, 9.8 downward. It gets to a stop at the top. The acceleration is not zero. The acceleration is still 9.8 downward, and then it starts to fall down. 9.8 downward, 9.8 downward, 9.8 downward, and it'll stay constant acceleration of technically negative 9.80 or 9.80 downward until it literally runs into anything else. So if you catch it, as soon as your hand touches it, it's not going to be constant acceleration. Or if you let it fall on the ground, as soon as it hits the ground, it's not going to be constant acceleration anymore. But all the other time, it's constant acceleration. Now, did that help you with your regards to your constant acceleration question?
It's mainly about trying to figure out the variables to a problem because I got immediately stuck on a question asking you for time.
Okay.
And yeah, and all you're given is, I believe, the end velocity and the end position, and then and then you just assume the both initial velocity and position to be zero, but they don't
Oh,
immediately give you constant acceleration.
but they want the time.
They want the time.
Okay. Then in that case, you probably want to use the
The
definition
V,
of
the V,
average
V zero plus
acceleration.
AT.
Yeah,
Oh,
V equals V0 plus AT, which also can be written as A equals V minus V0 over T.
the problem for me in that case was substituting A
Mhm.
to isolate T.
So, did you say they gave you the final
They
velocity?
did not give you an immediate constant acceleration, only that it's on constant acceleration. This is
Okay.
a running question.
So
Oh,
they didn't give you the acceleration, but they did give you the final velocity, the initial velocity, the final position, and the initial position.
yeah.
Okay.
Well, both initials are
Zero.
basically assumed
Yeah,
because it's a foot race.
gotcha. So, I'll do it right here. Our equations that you have are x is equal to v bar t. Uh, r you
Oh,
say plus x zero. That's one. Another equation we have is v is equal to v zero plus at. Another equation we have is x is equal to 1 half at squared plus v zero t plus x zero. And v squared is equal to v zero squared plus 2ax minus x zero.
I missed the second one. I thought there was like, oh God, the V's. No, the first. I missed the first one. The one with the average acceleration. And
Notice the very first one, that's average velocity, not average acceleration. That's a big difference there.
the average velocity. But
Well,
I think that's the one I'm looking for, isn't it? If you're not given an immediate constant acceleration.
yes,
Yeah.
these equations require a equals a constant. And I don't think I even mentioned this last one to you, but this last one's comes in pretty handy from time to time. But it's just basically if you have two velocities, it can be the velocity initially and then the final velocity, or it can just be some velocity, 3 seconds in and then another velocity 5 seconds in. You just add those two divided by two, and that gives you the average velocity. That happens to be the same as this average velocity. So that's often why this equation is so helpful. That and this equation for that matter. So I suspect you might want to use that because you can say this is the initial velocity, which is going to be zero. And then you can say this is the final velocity. So all you have to do is take and find the average velocity is the final velocity divided by two. And then you can plug that in here and solve for t.
Okay. Okay. Yeah. I straight up did not find. I somehow did not find the first equation in the textbook.
Gotcha.
Sorry.
Yeah,
Sorry, I burped. Yeah. That's probably why it stumped me.
really, this first equation, it's in the textbook, but it's listed as the average speed or average velocity.
Oh my God. That's
It's x minus x zero over t minus t zero. That's all it is. So I just replaced s with v bar.
oh my God. Oh my God. So 2960. Yeah, I think I have the equation now.
Yep.
This would be the one. This would be like the one thing. Oh my God, yeah, it is among them.
They're pretty straight.
Yeah, 13.3, yeah, it was that one. Yeah, because I was doing a practice quiz.
Well, don't get discouraged initially, especially when you're doing chapter two and a little bit into chapter three. A lot of it's about knowing what the symbols are in these equations and then
Yeah.
looking for equations that have the values you want and the values you have. And sometimes you have to combine two, like I did there. I had to take the v bar equals v plus v2 over 2, and I had to combine it with the x equals v bar t plus x zero. So
Okay.
sometimes you do have to use two equations. That's sort of the difference between what I would say high school level physics and college level physics. We generally have a lot more times where you're going to have to use multiple equations, multiple steps, and stuff like that to solve problems, especially in this course, which is the university physics, which is another echelon higher than the college physics that we normally would discuss.
I have not even taken any either previous two.
You haven't taken any physics before? Did you take any in high
No, absolutely not. I think the last science I took was college level chemistry.
school?
And
I
I
didn't
did
even
not.
take high school science. I did take chemistry in high school, but I failed it. So, I'm awesome.
Uh, yeah, I did not take any physics before this. I mainly have a computer science running track. So yeah.
Well, this will help you in all realms. It's just, good, clear thinking, remembering what things you know, how to
Yeah,
apply, you know,
remembering things, some basic things. uh, yeah, kinematics. The test is open for the asynchronous right now, right?
Yes, I went ahead and
You,
opened up online test one and online test two, and I haven't opened up the face-to-face test yet, but I will probably open them up. I always open them up 7 days
it
early.
says it's due the 9th of June.
Yeah, I had to move some of the dates just to make sure we fit everything in. So online test one is due the 9th, and online test two is due the 16th.
I
But
thought it was I thought it was due I thought both of them would do like a week before what it is.
yeah, they were. I just moved them back so that we would have so that you have more time basically.
Oh my
We
god.
had some
Okay.
students that haven't even gotten, for instance, their Pearson yet. Uh,
Okay.
so I try to make sure
I was fretting over the June 2 date. I'll be honest.
yeah,
Is
well,
it still due the 2nd?
no, it's moved back to the 9th and the 16th.
Okay, thank God.
Remember, and this part's important, so make sure you hear this. Online test one is chapters one and two. Online test
Yeah,
chapters,
it straight up says on the thing.
but
Yeah.
yeah, you want to try to take both of those before you take the face-to-face test, which is due on 6/9. So even though it's not due until 6/16, I would suggest you at least take it once.
Before that. Okay. But there is the option to take the face-to-face test for asynchronous.
Yes, yes.
Okay.
But the face-to-face
It's
test,
but it's not required. Face-to-face is not required.
it will be required, but not now. It's required by the 9th, and you will be given 7 days to do it. So it has to be turned on the second, and it'll be open from the second till the 9th, and you've got to find some day in that time period to get that done.
To actually come in campus and do the test.
Yes, or some proctoring facility. Yes,
Oh God. So both the online and the face-to-face
but not the online.
is
Online, you do anytime you want, anywhere you want.
and the online is open note, but not the face-to-face.
Open notes, open book, Google searches, all that stuff.
Face-to-face is none of that.
Exactly. Face to face is nothing. All you get's the equation sheets. Did you notice that I've got the equation sheets and the documents that you're allowed on the test? They're actually in,
Yeah, those are given.
yeah, they're also
Okay.
listed in the module that says helpful documents and links.
Yeah. Because I was about to be worried about the what was it, the calculus stuff.
Yeah, there'll be some of that and tables and stuff in the book.
Okay. Yeah, because yeah, I do not remember, especially not my integrals.
Well, the main ones you'll need is your trig derivatives and integrals, and your polynomial. So.
Okay, just those ones, and then just any extra information, like the length of a penny.
Yeah, you should have some, feeling for the world around you and how big it is.
Oh God. Oh
You should also
God.
have some idea of, what's the life expectancy of a human.
It won't be as weird as the Archimedes bathtub, right?
Right. Not quite that weird.
Okay.
But do you know the life expectancy of a human, or do you know how many
The
times?
expected is 80.
Yeah, so
The expected
9.25 is the latest data, in fact. But
it
you
took me a while for the penny. Because you said the penny was a centimeter big, centimeter in diameter, and then a millimeter thick.
yeah, about 1.5 centimeters in diameter.
Okay. Okay.
And how many times does a human heart beat in a minute?
70 a minute.
That's a good idea. Yeah, that's a good idea.
The other one was just the population of the United States. The given one in the thing said 300.
Yeah, that's old. I think we're up to 370 now, 370 million.
I think it was 340
Is
last
it?
I checked.
Right.
Well, that was 2024 though.
Hmm.
So my one, I'm gonna go like in a couple months. Yeah. Yeah, I think that's about it. That's about it. Just yeah, just the one kinematic that I missed.
Well, hopefully that helped you. I've already
Okay.
uploaded the notes to my Google Docs page, so it's available for you. And this video should be posted. I usually try to do it at nighttime, the same night, but lately they take so long that I'm not able to do it till the next morning. So either tonight or the next morning, this video will be posted for you guys.
Okay. Thank you. Thank you.
Well, if there's nothing left, I think I'm going to go ahead and split. You have any more questions before I leave you?
No. I'll just see myself out.
No problem. It's Adrian, right? Yeah, Adrian.
Yeah.
All right.
Yeah.
Have a good one, Adrian. Let me know if you need anything. Remember, you can always take screenshots of any problems you're trying to work and don't understand, especially if they're multiple choice. Make sure you get the photos of not only the question, but the multiple choice answers that are available. And you can just text them to me and I'll answer them as quickly as I can.
Okay. Thank you.
You can email it too, but texting is a lot more beneficial. I'm sorry if people haven't been able to get up with me with my email. I mentioned that in the email I sent out today. I'm having difficulties getting Microsoft Office Suite to sync my emails between my computer at home, my computer at work, my iPad, my iPhone, and inevitably mail is missing. So,
Yeah. It just gets it. It gets it every.
yeah, I'm sure I'm missing some of it, but some of it is just literally it's not showing in one venue, but it is in the other. There's ways where you can set whether you check the mail and if you leave the mail on the server, and I think that's the internal workings that I'm running into, and I don't know how to set that to the right thing on all the individual devices I use. So I suspect it's not a bug as much as it's me not knowing exactly what's going on with those. But the main thing is that's why I ask you guys to text me if you don't hear from me within one business day. So,
Yeah. Okay. Got you. Yeah.
all right.
See
Well, have
you.
a good one, Adrian. And like I said, feel free to contact me if you have any questions, email or text. Have a good day.